Hey guys! Today we are going to talk about arrays and bit manipulation. In the following problem, we are given an unsorted array in which there is only one element that appears only once. So in this example, 1 appears twice, 4 appears twice, 2 appears twice, and it's 3, as you can see. It does appear only once, so we should return 3. So how can we solve this problem? The first solution we may think about is about using maps. We could, for example, iterate on this wall array, and every single time we are going to put the element into a map. So we can create a map M and say, every single time that I'm gonna get an element, I'm going to add it. So here we iterate, so we are going to add 1, 4, 2, 1, 4, 2. And if the an element already exists into the map, we are going to delete it. So here we delete 4. We go on 1, we delete 1. And we go on 3, we put 3, we go on 2, we delete 2, and in the end, as you can see, the only remaining element, that's the single element, the element that appears only once in this array. So what about the time and space complexity of this solution? Regarding the time complexity, we have to iterate on the wall array. Because as you can see, the array is not even sorted, so we could not think about potential optimization for that. So in this case, we have to iterate over all the elements, so the time complexity is O of n, with n the number of elements in our array. What about the space complexity now? In the worst case scenario, we're gonna have to store all the distinct elements. So we're gonna have to store n divided by 2 items. So we can simplify this by O of n as well, meaning a linear time and space complexity. So as we said, we cannot improve the time complexity, but can we improve the space complexity? We can, but first we need to remind us a bitwise operator called the XOR operator. The XOR operator is pretty much simple. Let's take 2 bits, B1 and B2. If these bits are equals, then the result of applying XOR on these 2 bits is gonna return 0. Whereas if the 2 bits are different, B1 being different than B2, the result of the XOR is gonna be 1. So let's see how it goes on a simple matrix where we can see all the different combinations. 0, 1, 0, 1. So if we apply XOR on 0 and 0, because the bits are the same, it will return 0. And on 1 and 1, because the bits are the same again, it will return 0. And on 0 and 1, the bits are different, it returns 1, and on 1 and 0, they are also different, so it returns 1. So this is the result, the different result that we can get with the XOR operator. And we will see that the XOR operator has some interesting properties. The first interesting properties is the following. If we can do n XOR 0, the result is always going to be n. So let's take an example. If we do 101 XOR 0, the result is going to be 1 and 0, 1, 0 and 0, 0, and 1 and 0, 1. So 101, which was our initial integer. The second interesting property is the following. If we do n XOR n, it always returns 0. Let's see why. If we do 101 XOR 101, 1 and 1 the bits are the same, so 0, 0 and 0, 0, 1 and 1, 0. So it's pretty much obvious because every single time we are going to apply the two same bits, and we have said that if the bits are the same, it returns 0. So overall, n XOR n is equals to 0. The latest interesting property in our case is that the XOR operator is symmetric. What does it mean? It means that if we do A XOR B, it is equals to B XOR A. So we can apply the XOR operator on whatever order we want. We're gonna have always the same result. So now let's come back to our initial example. We had 1, 4, 2, 4, 1, 3, and 2. So what if we apply the XOR operator on every single integer of our array? We have just said that n XOR n is equals to 0. So if we do 1 XOR 1, it will return 0, so it kind of cancels both ones. And the same applies if we do 4 XOR 4 and 2 XOR 2. So if we apply the XOR operator on every duplicates, it will give us 0. And we will then apply the XOR operation on 0 and 3. And we have said as well that n XOR 0 is equals to n. So 3 XOR 0 should give us 3. So if we apply the XOR operator on every single integer, we should have, as a result, 3. So let's give it a try to see if this is actually working. But first, let's do a small utility table to remind us the binary representation of our integer we are going to handle. So we have 1, 2, 3, and 4, and 1 is 0, 0, 1, 2 is 0, 1, 0, 3 is 0, 1, 1, and 4 is 1, 0, 0. So let's apply the XOR operator on every single integer. So we will have 0, 0, 1, 4 which is 1, 0, 0, 2 that is 1, 0, 1, 0, 4 which is 1, 0, 0, 1 which is 0, 0, 1, 3 which is 0, 1, 1, and 2 which is 0, 1, 0. If we do a big XOR operation on every digits, what do we have? If we do 1 and 1, 0, so 0 and 1, 1. 1 and 1, 0, 0 and 1, 1. And 1 and 1, 0, 0 and all 0, it's 0. So we have 0, 1, 1. And if we see our utility table, 0, 1, 1 is 3. So we have been able to find the single element. Bear in mind that the solution is also working because the XOR operator is symmetric. So regardless of the way we iterate on the array, be it forwards or backwards or whatever we want, it will always return the single element, that is 3. So what about complexities? Regarding time complexity, we still have to iterate over all the arrays, so the time complexity will still be O of n. And regarding the space complexity, we do not have to store any extra data structure. We just use a temporary integer, which is the temporary application of the XOR operator on every single digit. So the space complexity is constant, so it's O of 1. So that's it, guys, for this video. So we have been able to find the single element quite efficiently in this example, but also bear in mind that when we have to deal with duplicates within arrays, sometimes it's very helpful to remind about the XOR operator, in particular because of these two interesting properties, n XOR 0, which is equals to n, and n XOR n, that is equals to 0. I hope you did enjoy this small video. If you want to get more information, you can go on solvingalgo.io, or you can even follow me on Twitter at Tiva, T-E-I-V-A-H. See you guys. Cheers.